them?
You do. You have godlike power.
I wouldn't call it that, and I will try to use it with discretion.
Well, that's God with a small g.
Yeah, well, reminds me of Nike, the goddess of victory and nice titties. All right, it is now after the start time in the latest tradition of fourth day punctuality. I welcome you to the fourth day 2021 Zoom. We just had the ceremonial starting of the recorder. So the first agenda item has been knocked off. I feel like we've accomplished something already. For those of you who don't know us so well, the Fourth Interest Group had chapters in the olden days. One of them was the Silicon Valley mother chap, if you will. And although FIG is long gone as an organization, the members on. The Silicon Valley Fourth Interest Group has these monthly meetings. We have an email chat list, although the administrator is not available to add new people at the moment due to his own personal circumstances. We have the FIG and SVFIG websites, and thank you so much to our webmaster, Dave Jaffe. So I recommend all those things to you. There's other stuff we'll get into later. The main activity I think I'd like to head us towards is this idea of scanning some of the paper fourth resources that are in our possession and getting them up on the web, or at least archiving them if there are copyright issues. I don't propose to get involved in this issue of copyright clearance. Is expensive and time consuming. So anybody that might potentially object to something will make a digital record of it and hold it to our chest. So the thing I need to do at this point, I guess, to find the schedule. I haven't forgotten, Greg. I'm going to email that to you as soon as I have a moment.
Thanks much.
So, Xuyang Chen. Sean, are you online at this time? That's an auspicious beginning.
You say Sean or Don?
Mr. Chen is the first presenter. He's the gentleman, I guess he was in the robot star. Oh, there he is. Good morning. Say your first name, Mr. Chen.
Shoe as in wear on your foot, and yang as in yang.
I hopelessly butchered the pronunciation. Thank you for correcting me. What we do here at Fourth Day, as all our other meetings, is you are responsible for introducing yourself. And also, are you ready to proceed?
Oh, I thought I start at 9:10.
Okay, but
yes, I am ready.
I can blather for 4 minutes if you'd rather.
No, I'm sorry if I was late, but yes, I'm ready.
You're not late. You're right on time.
All right, that sounds great. I'm ready.
I think that there was I've heard it attributed to a lot of people, but Vince Lombardi comes to mind as if you're if 5 minutes early, you're on time. If you're and so anyway, so let's light the fuse with our first printer. Introduce yourself and on with the show.
All right. Then without further ado, can everyone see this? All right, so a while ago you might have known me as Sean, but I don't like that name. I'm gonna change it. So if you have any English sounding American names, then do send them my way. I used to be in a robotics team, and I think I gave a few presentations about that about a year back. Well, now I'm in college. I'm not in that team anymore, and I've moved on to compilers. And so the topic of today's presentation is, and you might have already watched this from MovForth 2020, is pretty much just a MovForth compiler. Before I get in too much about it, get too ahead of myself. The problem I'm trying to address here is, I'm sorry, I didn't get much sleep last night. So the issue that I think has gone through the mind of a few MovForth programmers before is that MovForth could be faster. When you, I'm sorry. I'm sorry, let me start this over. Good morning, everyone. Without much ado today, I want to talk about compiling MovForth. In short, I've written a compiler for MovForth to address the problem of speed. And I think in the past, in a lot of older MovForth systems, what you would do if you think your code's not running fast enough, if you're doing too much stack juggling, is you write assembly. But evidently, when you write assembly, you lose both portability and readability, which is quite a bit of a problem. So I understand that there's a lot of MovForths like WinForth, MPForth. They heap the top of the stack into a register, and that's very good. But today I want to see what would happen if I converted the entire stack into registers. So there's no stack at all, no stack juggling. And before I get too much ahead of myself, why am I making another MovForth? Well, because I want to see because in the past, MovForth compilers always sacrifice something. If they're fast, then they might sacrifice portability. You might only be able to compile them to certain systems, or if they can run on many different systems, then they have sort of reduced primitives that don't take full advantage of the processor. But here I'm trying to satisfy all three of these points. And the way that there's pretty much the source of power that I'm drawing from is LLVM. And LLVM is not a very old library, but I think in the context of MovForth, it's a very new technology. In short, LLVM is a compiler, a code generator, and optimizer library, where as long as you can convert from your front end, from C, C++, Rust, or MovForth into LLVM pseudo-assembly format, then LLVM can take that, optimize it, generate it, link it, whatever you want into a platform of choice. And so as you can see here, it's pretty much the go-to library for a lot of new languages like Rust. And it's also very, very powerful. That's part of the reason why their logo is a dragon. Pretty much any modern general computing architecture, it does support. And so what I'm trying to do here is to see if we can convert from MovForth code into LLVM IR, which is the pseudo-assembly format. And then using the pseudo-assembly format, we can apply the same compiler optimizations and code generators used in something like Clang. Clang is a very popular C++ compiler. And so specifically, what I'm trying to achieve with compilation is to reduce the number of the overhead from the MovForth interpreter. And I'm sure a lot of us here do noticed that in certain forth words, most of the operation is stack juggling and compilation. And I'm not saying that registers are always better than the stack, but here I'm just trying to experiment. I'm trying to see if there are any performance gains at all by converting all stack operations into registers. And you'll see what I mean by this in a second. But in short, I'm just trying to achieve what most C++ compilers do, but which is to compile a very lean, stripped down, minimal piece of assembly or piece of machine code that does the same as the forth source. And so to this end, a goal I had before I started was to not have an interpreter in the final compiled code and to not compile a dictionary. And obviously, we will not have a stack in the final code. And the purpose of this is to see if pretty much the code gets faster. But an important point I want to make is that as I'm doing this, the forth source code does not change. To the programmer's perspective, there's still a stack, there's still a dictionary, and there's still an interpreter. But all of that optimization work, all of that abstraction is being done by the compiler. So one major feature that I didn't want to lose here is that programmer doesn't deal with any optimizations at all. All of that is done by the compiler. So you can take forth source, you can compile it to ARM, you can compile it to Intel, you can compile it to whatever architecture you want. The source code does not change. So one of the main challenges I had in doing this is that, well, obviously forth is stack based, and LLVM was originally designed to support the Clang compiler. So LLVM is built around the idea of having functions and having registers and having clearly defined control flow blocks. And forth doesn't have any of that. If I this main function here, which prints 42, I have no idea if it takes any inputs. I have no idea if it returns any numbers. I have no idea that even 42 is passed to the emit word. And so that's all of this is done by the compiler. It builds a data flow graph and does a lot of fancy what do you call it? You'll see. So you can see on the right in the pseudo assembly, the compiler has attributed the number 42 into the printf statement. And so printf here is just a debugging convenience. It doesn't really have to be printf, it can be any system call. Great, so let's make this harder. As I said before, for a forth word, you have no idea if it takes any parameters or if it returns any numbers. But as I convert from forth into pseudo assembly, I have to figure this out because pseudo assembly is based around a C-like syntax. And so you can see here, square is a function that takes one parameter as the factor as input, and it returns the squared value of the factor. And the compiler generates all the necessary instructions to do this. What is happening is that it's symbolically working through the execution tokens in the definition, and it's figuring out what the final state of the stack is. And so when it first runs into dupe, it realizes, oh, dupe takes one stack element as input. And so therefore, the word square must have one parameter. And likewise, at the end of the evaluation, it realizes that the multiplication word pushes two elements on stack. And so, or multiplication word pushes one element on stack, and therefore this word square must return one element. And this can get even more complicated, in fact, very complicated, if you introduce control flow into this, because in the process of naming these registers, the compiler has to know that, oh, the counter word must be conserved throughout the word definition. So it has to realize that counter is not being thrown away when the loop goes back to the beginning, but counter is actually being used repeatedly. And so as you can see here, its compilation is very beautiful. It compiles it down to a very minimal loop. And another thing I want to point out is it also generates basic blocks. So in the case that you are compiling a lot of branches into your fourth word, it figures out the entry point of each branch, and it basically divides them up into basic blocks. And one more problem we have, and I think some people here might have realized, is that do and loop are actually immediate words, and instead of actually executing, they compile branches into the code. And obviously, during compile time, the compiled code has no concept of an interpreter or a dictionary, and so we can't execute do and loop during execution time. And the only obvious way to fix this is to do compile time evaluation. So ironically, in this compiler, there's actually an interpreter built in. And what the interpreter does is it takes all the immediate words and it does all the necessary compilation and whatnot. And at the end, what you get is pretty much compile time the ability to generate things at compile time. So this is actually I think it was a very cool feature, very hard to do. Pretty much, if you have immediate words, you can compile anything you want to the dictionary. You can pre-evaluate literals. And anything you can do during execution time, you can do during compile time. And in my opinion, this is a lot better than C++ templates. In the C++ world, there's a concept called template hell, and that's because, well, in Forth, if you wanted to execute something at compile time, you would just write regular Forth code. But in C, there's a special template. There's special template semantics which are actually Turing complete, and they're very hard to parse over. And I think we do have time, and I can demo a bit of this. So all of the code is on GitHub. It's open source. Use it as you like, fork it, clone it, build it for yourself, change it, make a pull request if you'd like. And also what we have here is a few examples. And so I'll start with just a very first example we saw in the presentation, which is a simple emit. So we have a main word here which prints 42. And this compiler is not a sort of a shell or a REPL or an IDE of any sort. It's really just a command line tool. And if you want to integrate this into your own project for some reason, which would be nice, I would be very honored. There's also a C++ API for it. So I'll compile it here. It generates a lot of debug output. Don't be afraid. But in short, the first step of compilation is generating the pseudo assembly. And you can see here the optimizations have reduced this to a system called a print, which prints 42 literal. And so just to prove that this works, it does print. Oh, whoops, it does print 42. And sorry if anyone can't see this, I will make the font a little bit bigger. There we go. And for those of you who can read assembly, I can't read assembly, but I'm sure a lot of people here can. Here's the assembly. What the compiler actually does is it links this against standard C, the standard C library, but in the future I can make it support other things. And then just for just for completeness, here's the linked executable. And I think it's a lot bigger because we've linked to printf and whatnot. So something more complicated is swap. And so in this swap, you can see how it manages to allocate registers for each stack element. Oh, oops. And so here the code's very simple. We're just printing 1 and 2. So once again, I compile. And actually, this code is very simple. So once again, the optimizer has collapsed it down into just print statements. But as you can see, it does print what you expect it to print. All right, then let's do something more complicated. Let's do a loop.
Yeah, I have a comment.
Yes.
I'm using something similar to this, prepared for me by Henry Strickland, who I believe appears at some of these meetings with Fig. And I can use either Clang or what's the other one on a Raspberry Pi, and it sped up my code by a factor of 7 to 10. The code runs on a Raspberry Pi, grabbing audio from a radio receiver, filtering it for 400 tap FIR, and recognize bearings of signal direction. And it runs sufficiently fast using Clang or the other one. Is it CSS? I can't remember. I have a choice. Yeah, it's a great tool. I thank Henry very much for having provided me with that tool for my work. Oh yeah, by the way, he calls it a G4 transpiler, and maybe he has spoken to this group about it in the past already.
Yes, G4 compiles forth into C, and then it compiles to C. G4, I think G4 does have a lot of optimizations, but I think
but not enough. In the G4 does fast ITC. I've used all the different ones. Even the -fast is not optimized enough. Henry's transpiler, written with he used Python to do the translations, and then use the Clang. Then I use Clang to optimize, and it really goes about 7 to 10 times faster doing an FIR based application.
I've actually never heard of that. What's the name of the software?
Well, I talked to Henry Strickland. Maybe somebody in this club can tell you how to get hold of it.
Andy, I don't believe that Henry has presented this work here. It sounds interesting as well. We should probably reach out about it. But yeah, that sounds interesting.
Yeah, I actually didn't know about that. I thought I'd researched all of the Forth compilers before, but apparently not.
No, I can assure you, about 7 to 10 times faster than G4-fast.
So the thing was, at the Forth 2020 meeting, I made a small promise to have benchmarks ready by this meeting, but fortunately I didn't get around to that. But once I do get benchmarks working for this compiler, I will post it to the mailing list.
I'm sure Henry would be glad to share with you that the make file and all the other stuff he gave me to run on the Raspberry Pi.
I'd be very interested in that. Yes. So thank you.
I told him about this meeting, but I guess he didn't show up yet.
I met him in real life once. He was a great guy. All right. So without further ado, here's the loop. I've got mark and resolve just like in a regular Forth, and oops, I'm very sorry for that. And this is a somewhat unconventional thing, but I've got a while and repeative. It's in essence just a do loop. And so you can see here we've got a lot of literal words, and all of this is going to be executed at compile time. You're not going to see any of these words in the final compiled binary. And here's the pseudo assembly. And as you can see here, just like in the slides, all we get is a very lean, very reduced loop. At the end here, we've got a branch statement that goes back to the top. And just to prove that the executable does work, here we go. And it's very, very fast. I think we just went through about 1,200. And if I really wanted, I can make that number even bigger. Let's say 100,000. Shouldn't be a problem. There we go. Just printed from 0 to 100,000 in less than half a second. And then next, we've got a Fibonacci example, and the primary purpose of this example is to show how a lot of operations with a lot of stack juggling can be reduced to just very simple register operations. And Fibonacci is especially criminal to this because at the very essence of it, Fibonacci is just adding up two registers and putting the result in a third register. It's two operations really. But if you were to write it in Forth, you'd have 3 or 4 stack juggling operations, which in an unoptimized Forth interpreter would take much more time to run. But this is not an interpreter because, oops. Because Fibonacci has been compiled down to just 2 adds. Yes, 1 add to increment the loop and 1 add to actually do the Fibonacci. And if you're wondering what these phi nodes up here are for, it's merely just a symbolic thing, which LLVM will optimize into this assembly later. So here's the assembly.
Well, I have a question.
Yes.
Does your method involve unrolling loops where it can, tying up
It
a lot of
can.
numbers? Uh-huh.
It can. So the beauty of this solution is that I'm not writing the code generator and optimizer myself. Any optimization you can think of that Clang has, you can run on here. So yes, it does have loop unrolling. It's got all sorts of cool things. It's got a memory to register. It's got, I can't think of anything right now. I'm very sleep deprived. It's got struct unwrapping, all sorts of things. And here, just to prove that it works, yes. It's extremely fast. One thing I do want to say here is that the compiler right now only supports 64-bit stack elements. But if you want it to be 32, it's just a matter of changing one number. If I were to make this Fibonacci go for longer, then eventually the number would overflow back to the negative. And oh, this one's recent. There might be bugs here though. There are also memory operations, and there's nothing really special here. It's just memory. But for the sake of completion, I'll just compile it anyways. Yes. Okay, then back to your presentation. So at the end, this code is not very mature yet. It's just a proof of concept. But even after getting it to just barely work, it goes very fast. And so as you can see, using LLVM, our Forth source remains the same. But if I wanted to compile this code to ARM or wanted to compile it to a microprocessor, I can do that very easily without any changes at all. It's like Java. It's like write once, run anywhere, except we don't even have an interpreter anymore. It's just pure lean, mean, green executable code. But one point here is I understand sometimes a lot of people just want a simple interpreter to bootstrap off of because compiling is very complicated and you don't always have a powerful host machine to run the compiler. Sometimes you're on an embedded system and you just want to have unlimited access to your machine. And in that case, that would be a very valid time to use an interpreter. One sacrifice I am making here for a compiler is there are certain operations that I can't do. For example, in some forks to implement tail call optimization, you might just grab hold of the return stack yourself and just pop off the top of the return stack. You can't do that here because you can't assume that every target architecture has a return stack, or you can't assume that the return stack works in the same way. And if you still want an interactive shell with compile time speed, you can still do that. I think LLVM does support linking pseudo assembly on demand. So with a little bit of effort, what you can do is write an interpreter that's fully interpreted with compile ability tacked on. And lastly, if you want to call C or C++ functions from your forth code, that's possible too. And that's all. I hope the presentation, I hope the graphics spoke for itself because I know I stuttered a lot today. But yeah, are there any questions? The code's right there. The slides are here. Look at it, star it, fork it, change it, compile it, build it for yourself. It's really not that hard to build. It's just a few commands. Yeah.
That's really great.
Sean, is the you mentioned an embedding in C? Is there are you able to pass data across that gap? What does that look like?
I actually have not done that yet, but what it looks like is really just in the compiler code. It's really just telling LLVM, oh, I have a function that takes a 32-bit int, a 32-bit int, and a 64-bit int, and which returns nothing. And then I tell LLVM to call it.
Cool. And then
it's very simple. To answer your question, the only thing keeping me from writing the C ABI is how to implement it in forth, because I'm not sure how to make the syntax for that elegant.
It might be worth looking at GForth's ability to call into C is not too bad. You have to sort of label each of the types of the parameters going out, but yeah, there's many different ways to do that kind of thing.
Yes, I have actually seen that. They've got the weird syntax with N and D.
Could you pass those LLVM statements, just pass them directly on to LLVM?
I'm sorry, pass
well, from the source code, the forth source, and then you just give an indicator that you want the following LLVM statements to just go unprocessed onto LLVM. Would that be possible?
If you're asking about calling C++, just like verbatim C++, that's not possible.
No, I'm thinking you compile this into LLVM statements, right?
Yes, into pseudo assembly, yes. LLVM IR.
So wouldn't it be possible to have some statements or make a word that consists only of these statements directly, so that you could call C in that way?
Yes, but it would. So if you're asking if I can take this pseudo assembly code verbatim and just drop it into a string literal as such, yes, that's possible, but LLVM itself, that's possible, but I wouldn't do it because
That'd be a pretty tedious interface to use to bridge over. You'd probably want something more ergonomic, I would think. But
Okay, I encourage you to continue this discussion in chat, either direct or to everyone. In any case, we're running a little over right now. So Dr. Tang, you ready to go?
Yes.
All right, introduce yourself and light the fuse. Thank you.
Okay, thank you. Yeah, let me grab screen. Let's
Hello,
see.
Ting. Nice to see you again.
Yes, yes, it's a pleasure. Okay. Now